installing a two-circuit disconnect in place of the junction box, complete with individual ground and neutral bars, leveraging the existing 12.2 wire as the feeder from the main panel, and housing the ground fault circuit interrupter (GFCI) breaker within this disconnect setup could potentially meet the inspector's stipulations and negate the necessity for extending an insulated ground all the way back to the main panel. The essence of employing an insulated ground in this context lies in maintaining the isolation between the equipment ground and the equipment neutral. This separation is crucial for mitigating potential electric shock hazards. When a two-circuit disconnect is integrated, the ground and neutral bars are physically segregated within the confines of the disconnect unit. By repurposing the 12.2 wiring as the feeder line, what is essentially being created is a sub-panel configuration housed within the disconnect enclosure. Consequently, the GFCI breaker installed in this disconnect will deliver the requisite ground fault protection tailored for the pool equipment circuit. However, it is important to recognize that this particular resolution is not explicitly outlined in the National Electrical Code (NEC). Inspectors may possess specific reservations or interpretations that could influence the approval of this method. A recommended course of action involves several steps. Firstly, reaching out to the inspector to elucidate the proposed solution and solicit their endorsement before proceeding with any physical alterations. Secondly, thoroughly reviewing local codes to guarantee that the intended solution adheres to all pertinent local building regulations. Thirdly, consulting with a licensed electrician who can provide expert guidance and confirm that the installation fulfills all code mandates. It is imperative to emphasize that all electrical work should be executed by a licensed electrician and that strict adherence to all applicable codes and regulations is maintained to ensure safety and avert potential hazards. Consider the implications of the neutral and ground being bonded together at the service entrance. This is a standard practice in electrical systems. The purpose of this bonding is to provide a low impedance path for fault current to return to the source, which helps to trip the circuit breaker or fuse and de-energize the circuit in the event of a ground fault. In a typical residential electrical system, the neutral and ground wires are bonded together at the main service panel. This means that they are electrically connected at this point. From the service panel, the neutral wire runs to the various branch circuits in the house, providing a return path for the normal flow of current. The ground wire also runs to the branch circuits, but it is not intended to carry current under normal conditions. Instead, it provides a path for fault current to flow back to the source in the event of a ground fault. The ground wire is connected to the metal enclosures of electrical equipment, such as appliances and lighting fixtures, to provide a safe path for fault current to flow back to the source. If a fault occurs and the metal enclosure becomes energized, the fault current will flow through the ground wire back to the service panel, where it will trip the circuit breaker or fuse and de-energize the circuit. Because the neutral and ground wires are bonded together at the service panel, fault current can flow back to the source through either the neutral wire or the ground wire. This ensures that the circuit breaker or fuse will trip quickly and de-energize the circuit, minimizing the risk of electric shock. The requirement for an insulated ground wire to the pool niche is designed to prevent stray current from flowing through the pool water. Stray current can be caused by a variety of factors, such as faulty wiring, damaged equipment, or even nearby electrical storms. If stray current is present in the pool water, it can create a shock hazard for swimmers. By using an insulated ground wire, the pool niche is isolated from the rest of the electrical system, which helps to prevent stray current from entering the pool water. The insulated ground wire provides a low impedance path for fault current to flow back to the source in the event of a ground fault. This helps to trip the circuit breaker or fuse quickly and to energize the circuit, minimizing the risk of electric shock. Let's discuss GFCI protection in detail. Ground fault circuit interrupters, or GFCIs, are crucial safety devices designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit. If there is an imbalance between the outgoing and returning current, even a very small one, the GFCI will trip the circuit, cutting off the power. This imbalance typically indicates that current is leaking to ground, meaning someone could be receiving an electrical shock. The National Electrical Code NEC mandates GFCI protection in various locations, particularly in areas where there is a high risk of water exposure, such as bathrooms, kitchens, and outdoor areas, including swimming pools. The purpose of GFCI protection is to prevent electrical shock by quickly de-energizing a circuit when a ground fault is detected. A ground fault occurs when current leaks from a hot wire to a ground, such as a metal enclosure or a person's body. This can happen if the insulation on a wire is damaged or if there is a loose connection. GFCIs are designed to detect even small ground faults, as little as 5 mA, which is not enough to trip a standard circuit breaker but is enough to cause a dangerous shock. When a GFCI detects a ground fault, it trips the circuit within milliseconds, cutting off the power and preventing electrical shock. GFCIs are available in several forms, including circuit breakers, receptacles, and portable units. GFCI circuit breakers are installed in the electrical panel and protect the entire circuit. GFCI receptacles are installed in place of standard outlets and protect only the devices plugged into that outlet. Portable GFCIs can be plugged into a standard outlet and provide GFCI protection for any devices plugged into them. When selecting a GFCI, it is important to choose one that is rated for the intended use. GFCIs are rated for different amperage and voltage levels, so it is important to choose one that is compatible with the circuit being protected. It is also important to choose a GFCI that is listed by a recognized testing laboratory such as Underwriters Laboratories, all to ensure that it meets safety standards. Regular testing of GFCIs is essential to ensure that they are functioning properly. GFCIs should be tested at least once a month by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Common misconceptions about GFCIs include the belief that they can prevent all electrical shocks so that they can protect against overloads or short circuits. GFCIs are designed to protect against ground faults only, and they will not protect against other types of electrical hazards. It is also important to note that GFCIs have a limited lifespan and may need to be replaced after several years of use. The two-circuit disconnect is a specific type of electrical panel designed to isolate two circuits. It contains separate neutral and ground bars, which is crucial in this situation. By installing the GFCI breaker within this disconnect, you're essentially creating a subpole with isolated grounding, meeting the intent of the code. The 12.2 wire is being repurposed as a feeder. This means it's carrying power from the main panel to the two-circuit disconnect. This is permissible as long as the wire is properly sized for the load and the breaker protecting it in the main panel is appropriately rated. However, remember that this setup does not explicitly comply with the NEC. It's an interpretation of the code, aiming to achieve the same safety outcome. The inspector's approval is paramount. Consider the role of bonding in the overall safety of the pool electrical system. Bonding refers to the practice of connecting all metallic parts of the pool structure and equipment together with a solid copper wire. This includes the pool reinforcing steel, the metal pool shell, the metal parts of the pump and filter, and any metal ladders or handrails. The purpose of bonding is to create an equipotential plane, which means that all metallic parts are the same electrical potential. This helps to prevent electric shock by ensuring that there are no voltage differences between different metallic parts that a person could touch. The NEC requires that all swimming pool electrical systems be bonded together in accordance with Article 680. This article specifies the size and type of bonding conductors that must be used, as well as the methods for connecting the conductors to the various metallic parts. It is important to note that bonding is not the same as grounding. Grounding refers to the practice of connecting the electrical system to the earth, which provides a path for fault current to flow back to the source in the event of a ground fault. Bonding, on the other hand, is designed to prevent voltage differences between different metallic parts, regardless of whether or not there is a ground fault. Both bonding and grounding are essential for the safety of swimming pool electrical systems. It is important to ensure that all bonding and grounding connections are properly made and maintained in accordance with the NEC. Let's talk about the risks of not having an insulated ground. If the ground wire is not insulated and comes into contact with a conductive surface such as a metal pipe or a concrete wall, it can create a path for stray current to flow. This stray current can then travel through the water and create a shock hazard for swimmers. Additionally, a non-insulated ground wire can be more susceptible to corrosion and damage, which can compromise its ability to provide a safe path for fault current. The insulated ground wire is designed to prevent these problems by providing a barrier between the ground wire and any conductive surfaces. The insulation also helps to protect the ground wire from corrosion and damage. The NEC requires that all pool equipment be grounded in accordance with Article 680. This article specifies the type and size of ground wire that must be used, as well as the methods for connecting the ground wire to the equipment. It is important to ensure that all grounding connections are properly made and maintained in accordance with the NEC. Think about the potential for voltage drop in the 12.2 wire when it's used as a feeder. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or fail prematurely. The amount of voltage drop in a conductor depends on several factors, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the temperature of the conductor. The NEC provides guidelines for allowable voltage drop in branch circuits and feeders. It is important to calculate the voltage drop in a circuit to ensure that it is within the allowable limits. If the voltage drop is too high, it may be necessary to increase the size of the conductor or shorten the length of the conductor. In this situation, the 12.2 wire is being used as a feeder, so it is important to calculate the voltage drop to ensure that it is within the allowable limits. If the voltage drop is too high, it may be necessary to use a larger wire size. Consider the potential for inductive reactance in long wire runs. Inductive reactance is the opposition to the flow of alternating current caused by the inductance of a conductor. Inductance is the property of a conductor that opposes changes in current flow. Inductive reactance is more significant in long wire runs and in circuits with high frequencies. In this situation, the 12.2 wire is being used as a feeder, so it is important to consider the potential for inductive reactance, especially if the wire run is long. Inductive reactance can cause voltage drop and can also affect the performance of equipment connected to the circuit. There are several ways to reduce inductive reactance, including using shorter wire runs, using larger wire sizes, and using conductors with lower inductance. In some cases, it may be necessary to use a special type of cable with low inductance. Consult with a qualified electrician or engineer to determine the best way to reduce inductive reactance in a particular situation. Remember, this solution is presented as a potential workaround. Direct communication with the local electrical inspector is essential. Their interpretation of the code is what ultimately matters for approval. Any electrical work should only be performed by a licensed electrician, adhering to all applicable codes for safety and compliance. Ensure to thoroughly inspect all existing wiring for any damage or deterioration. Replacing damaged wiring is crucial for safety and reliability. Double-check the ampacity of the 12.2 wire to ensure it's adequate for the load it will carry as a feeder. Refer to NEC Table 310.15 for ampacity ratings based on conductor type and temperature rating. The GFCI breaker must be properly sized for the circuit. Using the wrong size breaker can lead to nuisance tripping or, more dangerously, fail to protect the circuit from overcurrents. Verify that all connections are tight and secure. Loose connections can cause arcing, overheating, and even electrical fires. Employ appropriate connectors and terminals for the wire sizes being used. Avoid using undersized or incompatible connectors, as they can compromise the integrity of the connection. Clearly label the two-circuit disconnect as a supplemental or remote disconnect for the pool equipment. This helps prevent confusion and ensures that future electricians understand the setup. Document all changes made to the electrical system, including wiring diagrams and component specifications. This documentation will be valuable for future maintenance and troubleshooting. The neutral and ground bars within the two-circuit disconnect must be properly isolated from each other. Ensure there is no unintentional bonding between these bars, as this would defeat the purpose of the insulated ground. Finally, before energizing the circuit, perform a thorough insulation resistance test to verify that there are no ground faults. This test helps identify any potential problems before they become a safety hazard. These additional details provide a more comprehensive understanding of the electrical principles and safety considerations involved in this type of installation. They also emphasize the importance of consulting with qualified professionals and adhering to all applicable codes and regulations.